All right, it's 8:30. Let's go get started. All right, good morning, everybody. How's everyone doing today? Good. All right, second to last week, and so last week's our final week, so I'm sure you guys are all counting down the days just like I am. It's been kind of a rough semester. Okay, all right. So the plan for today, I have your midterms today, so I finished grading those yesterday morning, and so you should see your grade on Canvas if you haven't already. Average on this midterm is about 40 out of 50, so you guys did really well. So definitely really good job. Really happy with this. Okay. And so definitely pick it up today. Check out the feedback I gave you, and then definitely use it in preparation for the final. The final is kind of right around the corner. Okay. So on Tuesday afternoon, I think I sent an email to everyone just with some information about the final. Also with the study guide and the practice final as well. So hopefully everyone got that. Okay. So just like I said in the email, please use the final study guide because I did cut out a lot of content from the class. So the final is going to be cumulative, just like I mentioned, but I did cut out a lot of stuff. It was mostly from the second midterm. So a lot of the second midterm stuff, since I just tested you on it, there's no need to kind of test you on all that stuff again. And so I took out, I think, everything except for Fourier series. And then for the differential equations, I took off a little bit of that stuff too. Okay. So definitely take a look at the final study guide. Definitely use that for you as you study. Definitely check out the practice final as well. It seemed like the practice midterm for this one was really helpful. So hopefully the practice final is useful for you as well. Okay. Logistically, so our final exam is going to be a little bit later in the week, so it's going to be on Thursday. The time for the exam is going to be 9 o'clock to about 11 a.m. Okay, it's going to be in here in this room. In terms of what you can bring, so it's very similar to the midterm exams. You can bring a writing utensil, you can bring a calculator, and since the amount of content on the final is about double the amount on a midterm, you can bring 2 cheat sheets. Okay, so 2 8.5 by 11 sheets of notes. You can use both sides. You can write whatever you want. All right, so I'll remind you of this, as we get closer, we'll be, I'm sure the final exam is on everyone's mind, especially starting next week. So, we'll talk about this kind of. But that's kind of the plan for the final exam. So the final exam is going to be very similar in format to the midterm exam. Of course, it's going to be a little bit longer, and so you can bring those. All right, and so for today, we're planning on going over hypothesis testing, and so I'm hoping to finish most of that today. So I think we barely started it last time, and so I want to make sure we get through at least most of it today, so that on Tuesday we can do last bit of probability statistics, which is regression. Okay. And then just like I mentioned on Tuesday, the plan for next week is that on Tuesday we have a regular lecture day, so that's going to be I'm still going to be probably finishing up the content from probability statistics. But then I want to reserve next Thursday to be just a review for the final. Okay. So next Thursday, no new content, just review for the final. Okay. And so, usually, for the last 2 midterms, I've recorded the midterm review video kind of outside of class, just because of time constraints. But I want to make sure that, for at least the final exam, we can have one class session for the final review, just so that you can ask questions, just so that you can kind of interact with it. And you can kind of, request certain topics, for the final review session as well. Okay. All right, and so that's all my announcements. Are there any questions I can answer before we get started for today?
Do you know how many questions are going to be on the finals?
So for the final exam, so for the midterm exam, we have 4. There's basically 4 short answer questions and 3 problems. For the final exam, it's going to be six short answer questions and 4 problems. So in terms of length, it's maybe about, I'd say maybe like 30, like a third longer than the midterm. All right, any other questions before we get started for today? Okay, all right, so let's go ahead and get started. Actually, let me scroll back up here. So I kind of want to start with this example. So this is the example that we kind of ended talking about on Tuesday. And so this whole section is about hypothesis testing. And so, first of all, I think we need to kind of define that a little bit better. And so, I think, hypothesis testing is something that, probably everyone's like, I already know how to do that. We've done, you guys have all done experiments before, you've taken lab courses. And so, I think everyone kind of knows what a hypothesis is, but there's kind of more specific mathematical theory in terms of, how we can test our hypotheses in the presence of uncertainty. Okay. So that's kind of the whole theme with probability and statistics in general, is that, a lot of what we observe kind of in the natural world is subject to kind of variance and is subject to uncertainty. Okay. And how we factor that into our calculations, how we factor that into our conclusions is something that's really important. Especially as you look at cases where there's lots of uncertainty. Okay. All right, so the example that we started with last Tuesday was that, let's say that we have an engineering application and we need to purchase these structural wires. Okay. And so, maybe, I think someone asked me after class, what is a structural wire? It's basically just like a cord, like a piece of thin metal that's used to support a weight. Okay. And so you can almost think of it as like a supporting wire. And so let's say that we're purchasing these wires, and the manufacturer for these wires say that, they can withstand 200 pounds of force or 200 pounds of load before they break. Okay. And we want to test that because, we want to use these wires for an application that requires them to support 200 pounds, about 200 pounds. Okay. And so what we want to do is before we place a large order, so let's say that we need to purchase, like 300 meters of this, that's a lot, maybe 300 feet of these wires. We want to test some samples to make sure that they can actually do what the manufacturer says they can do. Okay. Okay. Let's go ahead and start hypothesis testing. So let's So let's perform an experiment to actually see if this is true. Okay. And so just like I mentioned, right? So the manufacturers for these wires, when they say that these wires can support 200 pounds, it's not really a statement of like every single wire that they produce can hold 200 pounds. So throughout the manufacturing process of anything really, there's going to be some variance. There's going to be some, some wires that are more or less. Okay. And so what we want to see is that on average, can these wires actually support 200 pounds? Okay. 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 And so the steps that we're going to take to do this is kind of very kind of it's very kind of I would say it's just a systematic process. Okay. And so I'm going to do my best because some of the steps can be a little bit confusing, especially in terms of kind of understanding kind of why we're doing this step. And so, as we go through this, we're going to do a lot of examples. So I think I have 5 examples of this in total throughout the notes. I'm going to number out all the steps that we do, and then kind of do my best to kind of explain why we step. Okay, step 1. Step 1 for any kind of experiment is to form your hypothesis. So before you start any kind of experiment, you have to have some kind of statement or some kind of prediction of what you think, how you think the experiment is going to go. Okay? And that's your hypothesis. Okay? And so for this particular example, our hypothesis is that these wires can actually support 200 pounds before. So usually our hypotheses are going to take this kind of form. And so, strictly, the kind of experiments that we're going to be talking about in this class are strictly the ones where we're testing kind of a numerical value. Okay. And so another way to say that is we can express it as an equation. We say theta here, where theta is kind of the measured value. And theta naught here is the hypothesized value. Okay. So we're basically hypothesizing that the actual breaking point, or what we measure as the breaking point for these wires, is equal to what the manufacturer says it's going to be, which is 200. Okay. All right, so all of our hypotheses are going to take this form, and so it is a little bit narrow, and so of course this doesn't cover the broad range of experiments that you can do in reality, but a lot of the kinds of experiments and measurements that you would do as an engineer kind of fall into this kind of category. Okay, so it's strictly kind of a numerical hypothesis. Okay. All right. So after you form the hypothesis, the next step is I think a little bit strange. So this may be something that you may not be used to in your previous lab classes. So we have to form what's called an alternative hypothesis. And so what is an alternative hypothesis? An alternative hypothesis, you can almost think of it as a competing hypothesis, or one that's kind of almost opposite of your original one. Okay. And so the strict definition for it is that it's a statement, just like the original hypothesis, but it's designed in such a way that it can when the alternative is true, that can only be when the original hypothesis is false, and vice versa. Okay. And so you can never have a situation where both your original hypothesis and the alternative are true at the same time. It's always either one or the other. Okay. Okay. All right, so there's lots of different ways to form an alternative hypothesis, and so there's lots of different ways to do that, and we'll go over that kind of later in the class. But for right now, we're going to use what's called a left-handed alternative. Okay. So for this example, right? Remember this example, we're talking about the structural wire. Let's form an alternative hypothesis that says that the breaking point, or the amount of load that the wire can carry, is actually less than 200. Okay. In other words, we're forming an alternative hypothesis like this. Where, let me use the symbol. I guess I haven't defined it. Let's use the sigma mu. Okay, so mu here represents the breaking point. This is going to be less than 200 pounds. So that's our alternative hypothesis. Okay? And a lot of times, you form your alternative hypothesis kind of based on your application. Okay. And so if we purchase these wires, remember we want to use these for an application where these wires are going to support a lot of load. Okay. We're not really going to be upset if the real breaking point is above 200, right? And so if it turns out that the manufacturer made wires that are better quality than what we estimated, that's a good thing. And so then we're not really mad at that. But if it turns out that these wires are of less quality, where they can't support 200 pounds, then we're in trouble, and we can't actually use those for our application. Okay. And so for this application, it makes sense to have what's called a left-handed. We call this a left-handed alternative, okay, which is less than. Okay. Step 3. Step 3, we need to define something called the significance of this. Okay. So the symbol that we have for significance level is alpha. Let me write that down. So this step right here is really important. And this kind of goes back a little bit to our section on confidence intervals. Okay. And so significance level, this is basically a probability. Okay. Another way that you can think about this is that this is our tolerance. Okay. And so the significance level defines basically, the percent chance or the probability that our observations are actually, or I should say this. The significance level kind of defines the probability that our alternative hypothesis is true. So this is where we kind of bring in the factors of uncertainty. And so, we're going to be performing tests, right? And so what we're going to be doing basically for this example is we're going to ask the manufacturer to send us some samples of these wires, and we're going to test their breaking point. Okay. It could be, and so generally what we expect is that the samples that the manufacturer gives us, those are a good representation of the general quality of these wires. Okay? But there's a probability that what they send us is actually all bad wires, right? So there is always a chance, or there's always possibilities. There's always possibility that the measurements we take are not a good reflection of the overall behavior of the system. And so let's say, for instance, they send us 5 samples, right? So 5 sample wires. It could be that the five that they just happen to send us just all happen to be kind of bad, right? And so there's always bad luck. And so if you flip a coin 10 times, right, odds are you're going to get around 5 heads and 5 tails. But there is always the possibility that you flip 10 coins and you get 10 heads, right? And so whenever you have uncertainty, you kind of have to account for these kinds of situations where sometimes it just wasn't your day, sometimes it just you just kind of have bad luck. Okay? And so that's what the significance level represents. And so the significance level represents basically how much uncertainty are we allowing for in our results. Okay. And so mathematically, the way that this kind of forms, or the way that we actually use it, is kind of the first statement. So I kind of defined it a little bit backwards. Maybe I should have started with kind of the qualitative definition for significance. But the way that we actually are going to use it in practice is that we're going to define it as the probability that our alternative hypothesis is true. Okay. Okay. And so, because of that, we usually set our significance level to be something low. And so it's kind of the opposite of confidence. So if you remember the way we define confidence level, we define it as some high number, like 95%, 99%. For significance level, we're going to define it as the inverse. Okay? So it's going to be opposite of that. And so a significance level that's very common is around maybe like 5%. Just that alpha is equal to 0. In other words, what we're saying is that there's a 5% chance that the experiments that we perform, or basically the samples that we get from this manufacturer, there's about a 5% chance that they are not a true reflection of the true quality. Okay. 5% usually is a little bit high, relative to kind of more engineering experiments, but it makes the computations a little bit easier. It's 5%. Okay. Okay. All right, so significance level is really important. So it's not only important to know kind of how we use it, but it's kind of also really important to kind of conceptually understand what what it represents. Actually, let me pause here. Are there any questions on this so far? Yeah.
So I know the alternative and original can't both be true. Can they both be false ever?
No. So they're defined in such a way that one is always true, or
okay.
Or let me say this. And so there's always a result that we're happy with. And so for this particular example, if we do end up with a breaking strength that's like 210 pounds, then technically both the original and the alternative is false, but we're still happy with that result. It's 210.
Okay. So if you were to on an exam, if you were to say our original hypothesis is that something is between like 5 and 10, then alternative, if we were to give you the alternative, we can't say, oh, it's less than 5. We'd have to say it's outside of 5 and 10.
Exactly.
Okay.
Yeah. So that would be a two-sided alternative hypothesis. And we'll go over that kind of later today. Okay. Any other questions on this part here? Okay. All right, so that's step 3. So step 3 is define our significance level. Okay. Step 4, in the case where we were actually performing the experiment. So there's a couple ways that we can use this hypothesis testing. So the way we're going to use it in this example, let's say that we can kind of jump right into the experiments. And so step 4 is going to be perform your experiments or take your measurements. Another way that you can use this theory that we'll go over kind of in later examples is we can actually go through this whole process before we even start the experiment to kind of give us an idea of kind of what numbers that we need to actually hit in order to prove our hypothesis is true. Okay? But for this example, let's just say that we perform the experiments, and what we can obtain from the experiments is the measurements for the sample mean, the sample variance, and the sample standard deviation. All right, so for this one, let's say that we perform the test. I know, we're talking about this experiment and we're skipping the actual fun part, which is running the experiment. But let's just say that someone ran the experiment for us, okay? And we obtained the following result. And so the mean breaking point was 197 pounds. The variance is 36 pounds, and the standard deviation, which is just the square root of the variance, is 6 pounds. Okay. So this is for this particular example. If you're doing this kind of, for a different experiment, of course, you have different measurements. Okay. And then let's say that for this particular experiment, we did this with 25 samples. Okay? So we did 25 tests. All right. So from these results right here, you might look at this. And you might look at this this mean result. And that's usually what people look at, is they look at the average kind of result there. And they say that, 197, this is less than 200. And so, we can look at this and we can say, we should reject our original hypothesis, or we can say that it's false because the mean that we got is less than 200. And so, most of the time you would kind of stop here. And so you would take the measurements, you say that's less than 200, and say, we're done here, these wires can't be used. Okay. But we can't stop here because we are kind of talking about uncertainty, right? And so the question now becomes, we have this measurement and it looks like it's less than our hypothesis. And so it looks like it proves our hypothesis false, right? The next question we want to ask is this result here significant? Is it significant enough for us to reject our original hypothesis? Okay. Okay, so significance is really important because significance is what's going to basically count for our uncertainty, right? Let me give you an example. And so let's say that we have a dice, okay? So you're playing Monopoly for some reason, and then you roll the dice, right? So you roll it once, and you roll the dice and you get a 6, okay? And so, one thing that you can basically, one conclusion you can draw just from that one test is say that, this dice is rigged. It's always going to roll 6, right? Just from that one test. Like, obviously that's false, right? So the dice is a regular dice, okay? And so what you say is that, you need to, what the natural thing that you would say in the response that, you need to roll the dice, at least 10 more times before you can conclude, how loaded this dice is, okay? Unless you're playing with my cousin, then he does use loaded dice, and that's why he always wins, I guess. Okay, so the next step here, step 5, is to test for significance. Okay. Okay. So this step is it takes a little bit more to explain, and there's kind of a lot of stuff that goes underneath the hood, conceptually to kind of get to kind of a fair, what I think is a fairly simple calculation. Okay? And so in this step, essentially what we're going to do is to say that, you know, this variable that we're looking at, we're going to assign it as a random variable. We're going to say this is a random variable. Okay. So remember what a random variable is. And so a random variable, the way that it's defined is that every time we observe it, every time that we measure a random variable, its value can change, right? But it always changes according to a probability distribution. Okay? And so even though it can change, you know, it changes within some rules. Okay, there's some rules that define its you know, how it changes. Okay? Right, and so the next step is going to be to decide, you know, what kind of random variables is it going to be, or in other words, you know, we have to define its distribution. Okay? And so we really kind of have two options here. And so for a case like this, we're going to use our t distribution from last time. Okay. So the other random variable that we can use is the normal distribution or the Gaussian distribution. And so, you know, we'll talk a bit more later about, you know, how you would choose one or the other. But for now, let's just assume that we use the t distribution. Okay. And so to use the t distribution, we need the following formula. We have t is equal to x bar minus sigma naught I s squared. So all of these are variables that we've seen up to this point, right? So x bar is the sample mean. So that's what we measure from the experiments, right? So that was just from the previous step. Okay. Theta naught here, this is our hypothesized value. So that's the value that we think that this variable is going to be, or what the true mean is. Another way you can think of it. Okay. S here is the standard deviation. Okay. So that came from the previous step as well. And N, here's the number of samples, the number of experiments. We have everything that we need here. So let's go ahead and plug in. we plug in for everything here. So our sample mean is 197, our hypothesized value is 200, our standard deviation is 6, and we have 5 samples. And what we get from this is t is equal to minus 2.5. All right, so what does this mean? And so we got this number here, but we don't, it doesn't really have any meaning. Okay. So what this number basically means that this is basically the location on the probability distribution where our tests basically lie. Okay. Which is very vague and that probably means nothing. But it's one thing one way that you can think of it is that this is kind of a measure of kind of how far we've deviated from the hypothesized result. Okay. Okay. So now what we need to do is we need to compare this number. And so we'll compare this number relative to our threshold that's defined by our significance. And so we're going to use the same distribution function, so the same probability distribution. So I'd say this part is probably the weirdest part because it's we're going to be using the table, and so if you remember from the confidence intervals, we use the table for the t distribution. There's a table for the Gaussian distribution as well, so that's kind of where we're going to bring this. Okay. All right, and so to do this, we need to compute f of t. This okay. We're going to find f of t relative to our significance level, look up this value in the table, and then compare that to our measured value. All right, so let's define f of t to be 1 minus alpha, where alpha is our significance level. Okay. And so for this example, where we have our significance value of 0.05, we get an f of t of 0.95. Okay. And so just like we did with confidence intervals, we're going to take this number, okay, we're going to look it up in table A9. If you don't have the textbook, I'll post, I just realized that probably a lot of people might not have the textbook. I'll post the table for this online just so you can have it for the homework. So I think you need it for problem 3 on the homework, okay? So let's look this up in the table A9, along with our degrees of freedom. Remember, our degrees of freedom is n minus 1. So for this problem, we have 24 degrees of freedom. All right, so if we look this up in the table, and so for f of t is equal to 0.95 and 24 degrees of freedom, we get t is equal to 1.71. But since we did this step up here, since we did 1 minus alpha, okay, what we need to do is we need to invert this. So we basically need to take the inverse. And so we just take the minus sign of it. So we got t, the t significance is equal to minus 1.7. Okay. So I know I'm kind of doing a lot of steps here that kind of seem really random, but you know, there's kind of a lot of special cases. And so, you know, what I thought I'd do is like, you know, let's run through one example all the way through, and then we'll kind of go back and kind of reflect on each step and do kind of more examples. So right now, I know it kind of seems random that, you know, that I'm taking the inverse of this, but you know, we'll explain this more later. Okay. So what does this tell us? And so this t right here, you can think of this t as the threshold for t in order for our results to be significant. I should say the threshold for t where we can still accept our hypothesis. Okay. And so let's go back to our measure t. So our measure t measure was minus 2.5. Okay. So this is less than, or this is more a higher magnitude than our threshold. Okay. And so since this is past our threshold, what we can say is that, you know, our results, they are significant, right? So we took 25 samples, you know, that's a pretty significant number. And so what we say is that we can reject our original hypothesis, accept the alternative hypothesis. Okay. So the 25 samples we took was significant enough to disprove our hypothesis. Okay, but we have to put a caveat on this. Okay, and so the way that we got this threshold value was that we used a significance value of 5%. Okay, and so what this means is that, you know, we can reject our original hypothesis with 95% certainty. And so that last caveat is really important because, you know, whenever you perform an experiment, you know, you always have to account for the possibility that, you know, that you just had really bad luck. It just didn't happen. And so when you perform an experiment and you report the results, you have to kind of make sure you have that caveat that, you know, based on the significance level that we chose, you know, we can either accept the hypothesis or reject the hypothesis with a certain degree of confidence. Okay. And that's kind of the whole theme of this section, is that we not only do we have to report our results, but there's some kind of degree of confidence that we can associate. Okay. And this is basically the method that we use. All right, any questions on this example here?
So the threshold is like the minimum value that we have to reach. So
Exactly.
because negative 2.5 is less than, so they were both positive, then it would pass it, right?
Exactly.
Okay.
Yeah, and so if we measured something that was like, say that we measured the breaking point of like 210, then we get a positive t-value, and so that's going to be greater than the threshold. So then we wouldn't say. Yeah, that would be a case where like technically, we didn't get a breaking point that's exactly 200, but we're still happy with the result. We were able to reject the alternative. Any other questions on this example here? Okay, so I want to do at least one more example today, just because that process there's kind of a lot going on, especially at the end there. So I think once you kind of see a couple more examples, the methodology is a bit more quick. Okay. But before we do that, let's talk a bit more about alternatives, because a lot of this methodology here depends on how we define our alternatives. Okay. So our definition for the alternative hypothesis is that if the alternative is true, then we reject our original hypothesis. But if the alternative is false, then we accept the original. Okay, so it's almost like the dark side of our hypothesis. You can almost think of that. Okay. So there are three types of alternatives that we typically choose. And so the one that we did in the last example was a left-sided alternative. Okay, so for left-sided alternative, we have our measured value is less than the size value. Our right-sided alternative is the opposite, and so for the right-sided alternative, our measured value is actually greater than our measured value. Our measured value is greater than our hypothesized value. And then the two-sided alternative is that we reject basically on both sides. And so our two-sided alternative is that our measured value just is not equal to our measured value. Okay? Our measured value is not equal to our hypothesized value. And so for the two-sided alternative, if our measured result is either too low or too high, then we reject it. Okay? And so depending on the type of alternative that we choose, it kind of changes our methodology a little bit kind of for everything kind of past that step. Okay? And so it kind of changes how we use the significance level, it changes how we use the distributions. Okay. And so there's all kinds of subtle things. Okay. Okay, so I want to do another example for the right-sided alternative, and then we can kind of see how that changes up the rest of the methodology. Okay, so this example is going to be a little bit more dry, and so it's not going to be as physical an example as the last one. Okay, but let's just say that we have a random variable. Let x okay. So this example, it's not as fun as the last one. If you can even define the last example as fun, but I think I want to bring this example up because I think it kind of strips away all of the stuff and it kind of gets at just the heart of the process. So this is kind of that's kind of the point. And let's say for this random variable, we actually know the variance beforehand. So we don't have to sample it. So we just somehow we know the variance before we even start. And let's say the variance is now. All right. And so our hypothesis, the hypothesis that we have for this random variable is we think that its true mean is 24. And so what we want to do is we want to test this hypothesis. Let's say that we want to take 10 samples. So using 10 samples, let's test this against the right-sided alternative. Okay, so let's run through the same process that we did for the initial example for this one. Okay. The big difference here is that we're using a right-sided alternative instead of a left-sided. Okay. Okay. So the good thing is that a lot of the steps are already done for us. Okay. Let's just kind of write them all down just for completeness sake. Okay. So step one is to form our hypothesis. So that's done for us. And so our hypothesis is that the true mean for X is 24. And so the way that we can put that in variable form is theta naught is equal to 24. Okay. So our alternative hypothesis is that the true mean is actually greater than 24. Okay. And so what we can say is that theta is greater than. So step 3 is our significance level. Okay. So remember, the significance level is the probability that our alternative is true. Okay. And so this is something that we assign. Okay. And so it's you can almost think of it as the amount of uncertainty that we're allowing for in the results. Okay. And so just like the previous example, let's set a significance of 5%. So let me pause here for a second because we can give a little bit more context for significance level now that we kind of understand all the different alternative hypotheses. Okay. So remember, the alternative significance level is the probability that our alternative is true, right? And so one way that we can kind of formulate this mathematically is we could say the probability, big P, of theta being greater than 24, okay, is equal to 0.05. Okay. That's essentially what we're saying with the significance level. Okay. On the flip side, if what we're saying is that our alternative hypothesis has a 5% chance of being true, okay, or that's what we're testing for, then there is a 95% chance that our original hypothesis is true. Okay. So our probability that theta is actually less than or equal to 24 is 0.95. Okay. Just purely by process of elimination. Okay. And so if our probability for being greater than that is 5%, then the probability of being less than or equal to that is 95%. All right, notice how this is defined here, right? And so the probability of some random variable being less than something else, right? This is exactly how we define our cumulative distribution function. So that's really nice because what we can do, so these cumulative distribution functions, and so the tables that I've been mentioning, up to this point, table A9, table A8, what those basically are is those are the tabulated values for the distribution function. Okay. And so we can do, and so this is exactly what we want right here. Okay. So what we can do is we can look this up in the table. We can look this up in the table to get our threshold for T. In other words, our significance threshold. Well, that's exactly kind of what we did last time, right? So last time we looked up that significance threshold from the table. Okay. And so for this one, so this problem is a little bit different than our initial. So what was unique about this problem was that we knew the variance beforehand, right? It's not something we actually had to test. So we already knew. And so for these situations where we know the variance beforehand, we can assign a different random variable to this. Okay. And so for cases where you know the variance, we can define it as a normal distribution or a Gaussian distribution. Right, so for the first example, we didn't know the variance beforehand, so we had to measure it based on our experiments. Okay? And so in those cases where you have to measure the variance, you use the t distribution. That's table A9. Okay? But for cases where you do know the variance beforehand, you can use the normal distribution, which is table A8. And I'll provide both tables. I'll post it on Canvas. Okay. And so if we look up table A8. So look up table A8. In this case, we have an f of t. We have an f of t of 0.95. And our degrees of freedom in this case is 9. Remember what we said beforehand is we want to take 10 samples or 10 tests. Okay. You get a threshold. A threshold value of 1.6. E. Okay. So that's good. So we're going to keep it just like that. Okay. And so now let's take this threshold value and let's plug it into our formula that we had above. So, this example is kind of different in another way too. So in this example, we're not actually going to perform the experiments. Okay? And so this is a calculation we're going to do beforehand. Okay. And so since we know the variance beforehand, one thing we can say is that, we can kind of predict ahead in our experiment. Right? So when we run our experiment, what we can say is, what value for the sample mean do we need to get in order to accept our hypothesis? Okay? We're going to use the same formula that we had above, except we're kind of using it in a slightly different. So we're going to have t threshold is equal to sample mean minus hypothesized value divided by standard deviation divided by square root. Okay. The difference here is that we're going to rearrange this equation and we're going to solve for it. Because in this case, everything else in this equation is known. Okay. So we have the threshold value. We just looked that up in the table. We know our hypothesized value, theta naught, that's 24. The standard deviation we know, we're just going to take our variance and take the square root. And we know that we're going to take 10 samples. Okay? And so let's go ahead and plug all that in. And so we get is sigma is equal to E threshold times sigma over square root of n plus sigma. And what we get is 25. Alright. So what does this tell us? And so this tells us that if what we measure, so from our experiments, if we get a sample mean that's less than 225.56, then we can accept our hypothesis. That's less than. So this one we kind of did a little bit of the reverse, and so we didn't actually run the tests, but what we did beforehand was that if we were to run the tests, this is what we need to get in order to prove our hypothesis true. Okay, so this can be useful as well. Okay, so in cases where you know the variance beforehand, you can kind of already know before the experiment what you need to get. Okay, and oftentimes it's not as close to the hypothesized value as you think. Okay, sometimes it's a little bit off. You have a little bit of leeway because of the uncertainty that exists. Okay. All right. Any questions on this here? Yeah.
That's a theta, right? The leftmost value that we saw.
Oh, yeah. Supposed to be theta. All right, one last point that I want to make before we go. Okay? And so it kind of has to do with how we use a significance level. Okay? Because if you go back to our original example, when we computed our threshold, okay, we took the inverse of it, right? So we found our threshold and we just took the negative, right? So for this example, we did the opposite. So we didn't take the inverse. Okay? So we just kept threshold as a positive number. The reason for this kind of has to do with how it's defined, right? So I mean, one thing that you can say is that if you have a left-sided hypothesis or a left-sided alternative, you just take the negative of it. Okay, so I think that may be the easier way to remember it. If you have a right-sided alternative, then you just keep it as positive. But it's the reason we do that is kind of how it's defined. Okay. And so for a right-sided hypothesis or a right-sided alternative, we define this probability in this way, right? So the probability that our hypothesis is true is this, okay? For a left-sided alternative, so for a left-sided alternative, what we have is that probability that theta is less than theta naught is equal to the significance value, okay? Which is the opposite of this. So technically speaking, you could compute the value of the threshold from this, okay? Okay. If our tables were a little bit better, then you could. But let me show you the table because I think probably you've never seen that table before. So the reason we can't do this, the reason we can't kind of define the threshold directly based off this, is that our tables actually don't go down that far. So let me show you. So let's go to Dropbox here. Files. So this is the file that I'm going to post online for you. There's actually going to be the sheet that I'm going to give you for the final exam. So here you have the Laplaces, so I'm sure that gives you good memories. It's this table. But here's the t distribution. Okay. And so the way that you use the t distribution is that you look up the degrees of freedom that you have, as well as the ft value. Here they have f of z, but f of z, f of t is the same. As you can see from this table here, the lowest that this actually goes down is 0.5. It doesn't actually go down lower than that. Okay. And so if you have a significance level that is 0.05, and you're trying to look for that in the table, it just doesn't exist. You're not able to find it. And so the way that you actually use that is you look up kind of the inverse of that. So you do 1 minus significance. Okay? And so you can see right here we have a row for 0.95. Unfortunately, I can't mark this. But let me go zoom in on it. Okay. Pixelated as hell, but you can see that we have a row for 0.95. Okay. And so what you do is then you look up the row for 0.95, and then you take advantage of the fact that this cumulative distribution function is symmetric. Okay. And so you look up the value for 0.95 and you just take the negative. So that's all we did in that first example. So because that 0.05 didn't exist in the table, we did 1 minus that. We looked up that value and we took the negative. And I can show you that value right. We can see that for 24 degrees of freedom here, as well as an f of t of 0.95, we have 1.71, which is the value that we used in that first example. Okay, but since we did 1 minus significance there, we just took the inverse of that, so we took the negative. Okay, so I know it's a lot to kind of take in, definitely, as you're doing the homework. So this is basically what we need for problem 3 on the homework. Okay, so as you're doing the homework, read over the 2 examples that we did. It kind of takes a lot of kind of reading it through and kind of talking to yourself to kind of get this down. It's a lot of kind of jargon. It's a lot of kind of stuff that kind of seemingly is kind of pulled out of it. All right, any final questions on this? Okay, right. So I wanted to end a little bit early to give you a chance to pick up your exams. So I have your exams here. You're gonna come pick it up. So remember the average on the exam was 40 out of 50. So you guys did really well. If you have any questions on the exam, if you want me to look at something I've graded, or if I added up the points incorrectly, please let me know as soon as possible. But if not, thank you guys for coming today. I hope you guys enjoy the rest of your weekend, and I will see you guys next week. Alright, Austin, any final questions before I close Zoom call? All right, I'll see you guys next week.